last
Okay.
one for a little bit because we got CoinGeek, and then I've got a trial.
Okay, so, big trial. Okay. Sounds fun. Okay, let's get the small show started first. So, everyone, welcome to another episode of Bitcoin class with Satoshi, Dr. Craig Wright, and this is the last one before the CoinGeek. So we'll see what are we going to learn today, Doctor.
Okay, so there have been a few write-ups following your blog on the sort of formation of how we do state and maintain a Turing complete script. I see there's still a little bit of misunderstanding that people have, that they still have this misapplied concept that Turing completeness means infinite. That actually goes to Hopper and a number of others in the 60s. So a number of textbooks started erroneously putting that information in the 1960s, and since then Unbounded and sort of infinite have been mixed. And that's a problem because they're not. Remember, the nature of a Turing machine is that any computation that can be done in any way. So whether it's a human, whether it's DNA, etc. Now, some things may not hold, but they're not actually Turing complete. They're not computable. That's where people go wrong. You don't need to go to eternity and go, this never halts, therefore it's not a Turing complete script. You only know that it's Turing complete when it halts. So if it doesn't halt, it's not actually Turing complete. It may be, we don't know. That is the halting problem. We can never know. All right, so in this, I sent you a little bit of some links to some early material on perfect information games. Now, these are much easier than imperfect information, but we can, of course, incorporate imperfect information games into Bitcoin as well. And I'd like you to think about that for a moment. How do you think we could actually do some forms of imperfect information?
The first, I think it's just the first thing that came into my mind, just out of know, is when you talk about it reminded me of miners, because they may not know what others are doing. But you can also have a collaboration.
Correct.
Between some of them.
So we can actually have ways of aligning information, such as via hashes, for instance. This is some of what proof of work does. It allows the alignment of information, but that's incomplete. So there are a variety of types of incomplete information. There is the stuff that everyone knows of, which is the known unknowns. Now, a known unknown, of course, is we know something that we don't know. That seems sort of a bit antithetical to many people in itself. But then the more insidious version of an unknown information is the old Rumsfeldian, Donald Rumsfeld, unknown unknowns that everyone talks about in politics. That is, we don't know what we should know, and we don't even know that we don't know what we should know. So I'll give you an example. If we are completely underestimating an opponent, and the reality is we're blissfully unaware that we're about to be completely, utterly wiped out. This can be through ignorance or other sort of errors, but an example would be the Russo-Japanese War, 100 and a little bit years ago. At this point, the Russians didn't bother finding out anything about the Japanese or how they'd actually created more of their society or built up something beyond where the Russians believe they were. Now, if you start thinking about it that way, what you see is suddenly the Russians rush in their empire of thinking silly Asians, all their rhetoric about racist rhetoric, and then they got the shit beaten out of them.
Yeah.
Why? Because they didn't bother to find out. That should have been a known unknown. I mean, it should have been, we know that they're arming themselves, we don't know how much. But instead, they were completely ignorant of everything. So many of the other things that we don't even know are coming. Now, innovation is a good unknown unknown. I mean, I know government loves to plan things, but I've gone through this one before. The concept of the wheel, yeah. Yeah, Grund over there is inventing the wheel, and of course, old Barney comes up and does the, oh, when are you going to have it ready? Oh, I should have this innovation done, blah, 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 all that sort of stuff. Well, if you can describe how to invent something, then you've invented it. So that problem. So we don't actually have that knowledge. I mean, this is where innovation goes wrong. There's incremental innovation that everyone can predict, and then there's Schumpeterian changes that actually recreate capitalism and realign it. Now, what I want now to get you to, I gave you a couple sort of areas of complexity study. And in particular, I gave you some nice little 1978 thing on complexity of two-person perfect information games.
Yeah, nowadays, if you write in paper, use this as a reference. People say it's pretty like outdated for whatever reason. Yeah, but anyway.
I know, they're all old, except who cares, because it's mathematics. The stuff of Pythagoras is still used. No one references it anymore, but about 3,000 actually. So now, in these references that I sent you that you can put out to people, I've done undirected edge geography, which is an extension of a simple geography game. I don't know if you remember any of this stuff from university.
Geography game, such as
this is a graph problem. Nodes, vertices. In the modified version that I sent you, it's an undirected edge geography game. So that means what you have is every time you traverse an edge, the edge is removed out of the game. So if you've got a series of nodes, every time you move over an edge from A to B to C, the edge is removed and can't be reused. Now, in the particular game, if there is no way for one of the players to move, like all of the edges have been destroyed, then that player loses.
Okay.
Now, these are very simple games. Some of these have been played by children, and others have been modified to be mathematical problems, because that's what mathematicians do. They take simple children's games and even things like chess, and they totally screw them up and make it so that no one can understand them. That's what math is for.
Pretty much, yeah. If you read the paper,
but
it's much more
if you start looking,
go ahead.
Yeah. So if you read the papers, what you will find is there's a number of bits of information around what does and doesn't exist. And all of that, for instance, can be built into a script. Now, if you've got two players, So say we've got two players. We could make more complex games, of course, but this can be a sequential game, as happens. Can be simultaneous as well, but that's more complex. But say we're playing this sort of geography game, and as we're moving across nodes, I send you a updated version of a transaction. You then respond. Now, the way that each of us will do that is we only allow ourselves to remove one edge as we move. It has to be valid. There has to be something that comes out of this so that it's no longer going to be valid. And if we've constructed the game correctly, either through sort of linked transactions or in script itself, then each stage can lead to something that comes to an end. And by an end, I mean only a single player can win. So if you think about this, I send you, you send me, and people have looked. I mean, an example would be chess is a fairly simple game. In some ways, far simpler than the examples presented in the perfect information games that I've sent you. So you move, I move, you move, I move, and eventually one of us either quits or can't move or has a king taken or something like this.
Mm-hmm.
All of which is doable. For instance, a king that can't get out of the way, you could actually have it so that information is leaked, and the other player now can take the what do you call it, the script, the transaction, and assume the sort of position if there's no other way of moving.
Mm-hmm.
So, how much did you do of this sort of discrete mathematics and computer science or informatics when you did university?
I think so I think most of the discrete math I take it, and also
Uh-huh.
computernetics, yeah, but
Yep,
numerical
cybernetics.
methods, yeah, numerical methods, but
Mm-hmm.
so I'm probably a little bit better than Vitaly
How
in
much do you
management.
remember is a better question.
Oh, not much, unless
Well, that
I
doesn't
have
say
some,
anything.
yeah, unless some really engineering issue, I have to go back and check. But yeah, unless I use it, I forget. It's probably you
Mm-hmm.
remember everything, but most people they just if you don't, it's like a language. If you don't speak it often, like
Well, well, this is the whole thing. Don't stop studying.
mm,
I mean, I keep going back and relearning and relearning and relearning, so that's why I
mm,
don't forget.
mm,
So if you don't sort of put your books down and think that your exams are over and go home, and you expect, well, just to keep studying more of the same, then not only will you learn more, but you won't forget everything.
mm, yeah, like this
Yeah.
Turing machine or
Anyway,
NP complete. It's just
so
mm,
mhm.
yeah, keep going.
So, I mean, one of the examples of things that you've already incorporated is a simple version of Conway's Game of Life.
Mm-hmm.
So Conway had a Game of Life, of course, but if you can do all that sort of stuff, you can also build other games in. Now, if you've looked at that paper I sent you, what you'll notice is um, you're not going to find a polynomial time algorithm that's going to sort of decide this game for you. They're NP complete, and many of them are p-space complete as well.
Mm-hmm.
So effectively, you can have nice complex games that no one's going to have any idea of how they're going to end. Now, what that allows you to do in creating what seems to be a simple script is to create really complex outcomes. Now, so I'll give you an example. Traveling salesman once again.
Mm-hmm.
We can go back to this, we can form the node, and we can set rules. If we get rid of, what do you call it, routes, like between the original geography game is you can't use the node twice, but later versions of the geography game include combinations of that. So now if we're not going to two places twice, we don't want to go through things, and that becomes game like traveling salesperson solution games. And yes, we can argue, oh, there's approximations and all this sort of junk, but I mean, if you think about the cost of, well, doing this sort of work, then an approximation's only going to get you so far.
Mm-hmm.
So what you now have games such as this that can be um, p-space type algorithms that instead of the difficulties in computation that we have right now, you can move into multiple transactions. So do you want to tell me the difference between sort of the general time versus space trade-off?
Oh yeah, it's a lot of times this appears in like a programming or computer science. You have two choices. Either one is you compute things on demand on the fly, so you don't have to remember them. Then you have taken much more time, but you get less space versus another end of the spectrum, right? You kind of compute it once, then you can remember and you can store it, kind of like a cache, right? So whenever you see this again, you just simply look up. You don't have to recompute. But this, of course, because you have to store everything, so it costs more space, but it takes less time.
But there are other overlaps between those two. So remember, in parallel computation, there is also a memory trade-off. So one of the things we can do is, rather than making more complex programming that is, well, more depth of time in trying to get as much as we can into a single program, we can split the program into lots of little pieces.
Okay.
Now, I'm not going to discuss this before I go away, but we've talked about shadowing, for instance.
Okay.
You remember what that was?
I think it has different meanings in different contexts. But can you specify what shadowing you mean here?
Say in gaming, where we're talking about like game shadowing, where we want to have the ability to hide something.
Okay.
Like two people may enter a room at the same time in a gaming room.
Okay. So it's different from shadowing a variable. Okay.
And
in some programming languages, that's different context.
yeah, so basically we want something that is kept secret, as an example.
Okay.
Now, when we're doing that, and we're keeping those secrets, if you think for a little moment, that means we have the sort of capability to have two individuals enter at approximately the same time, and whoever's first can get access or can grab something, but equally the other one can't, which means we can start building distributed systems.
How?
If we have multiple nodes all having the same information that we have a consensus across, whoever sees the information first, that updates, it reflects through. But once someone has definitively sent out a transaction saying, hey, I've got this, the other one will no longer get it.
Mm-hmm.
So let's start thinking about that in Bitcoin terms.
Mm-hmm. So almost like it reminds me of like a multi-threading programming, but now you kind of use Bitcoin as like a signaling or a log.
Mm-hmm. Yep. So yeah, imagine now that we have multiple sort of different ways of finding information, multiple ways of calculating things, etc.
Mm-hmm.
Now we can hide all of this, of course, and what that now allows us to do is one player can discover and the others don't. We can stop cheating, for instance. We can ensure that people find aspects of the game but others don't. If someone gets to an area, others won't get there.
Mm-hmm.
Remember, it stops us. It stops people from cheating in games, and it goes more than games. So something that Silicon Valley and even Wall Street won't like, as an example, we could have a share trading system that limits the ability to algorithmically trade shares.
Mm-hmm.
Imagine, for instance, that we put a cost of trading built into some sort of share that we have.
Cost of
If you keep
trading.
the thing for 30
Mm-hmm.
days,
Mm-hmm.
um, keep it for 30 days, and your exchange is going to be inexpensive. Change it every 30 nanoseconds and try and arbitrage and pay a lot of money.
Mm-hmm.
Which one of the problems, of course, with shares is if you do the current thing of changing them every 2 minutes, then no one holds it for the long term, and the long-term investment actually loses money. So you can actually build a security that punishable for arbitraging your shares.
Mm-hmm. I think yeah.
Now,
Crypto
going back
traders.
to, sorry?
Crypto traders, they play a lot of
Mm-hmm.
like this kind
Yes.
of stuff. Yeah.
Yeah. I mean, as an example on that one, you could have it so that you could use money, require 10-minute settlement, break it down into 1 cent pieces. You don't need to worry about change because no merchant's going to be flipping 1 cent pieces as change that quickly.
Mm-hmm.
But going back to the other aspects, so some of the other things we've talked about include, like with Robin signatures and, say, commutative encryption. So, can you tell me what you remember from commutative encryption? And most
Commutative.
encryption algorithms aren't commutative.
Mm-hmm. It's if I remember correctly, basically if you apply two encryptions, let's say encryption A and encryption B, then if you usually you cannot reverse the decryption order, right? Has to be decrypt. You have to decrypt B and then decrypt A. It's like something like a Russian doll,
Yep.
onion, right? But communicative is you can in different order. So is that correct?
Correct. So with all of these things, we can build in how we're going to sort of solve something. It could be a combination at the same time. So a Pollig-Hellman scheme is similar to RSA, but it's going to allow, like RSA, commutative decryption. On top of that, we can have things simultaneously encrypted and not encrypted. We can build a combination of what we're talking about with perfect information games, a bit more complex by incorporating like card dealing algorithms. So if you remember some of the things I've mentioned in the past, we have an ability to securely deal cards.
So this is
I mean,
this is considered instead of the paper
it's
you
not
sent me.
only my gambling background.
It's not. This is considered.
Trying to get you to.
This is not the perfect information in this case, right? Because like you don't know your
No, but that's why I'm
opponent's
trying to get you to
cards.
think about how you can integrate both. Then, of course, to give you something else, we can obscure information. Remember XOR, we can split information. XOR can also split things, so combination of that and with 42 and key sharing, we can then have shared encryption. So if you start putting all this together, we can build something that enables hiding information, moving around, etc. So, do you remember? You probably don't remember any of the old games like Hero or Venture Quest or like the early Ultimas before they became what they are now, or anything like this?
No. Okay, not this this name I never heard about.
What? All right. Well, Venture Quest was an early game. I'm old, so.
You always say about Quaker.
Yeah,
Quaker. That's the only one I heard. I looked it up. Yeah.
Yeah. Well, still better than Buckaroo Banzai, which I sort of cut my teeth as I did. Was it Epic Games or one of those in Australia? This is God knows how long ago. I can't even remember. Early '90s. I did code testing and all that sort of BS for those guys, and that was a terrible, terrible, terrible game. That's all I have to say. But anyway, going back to the other, if you think about how you actually integrate this information in games, I mean, the images and design can be much better now than it ever was in my era. But equally, what we can now do is we can have that information so that people can not play on their home machine, but across big areas. Now, a problem that is still there that I've mentioned many times, World of Warcraft, for instance, other online games that I'm not really up with anymore, people still sell game equipment. So you've still got people who mine, get gold, do silly things, work in sort of game farms and sell information to silly Westerners who pay to up their character levels and all this junk. Now, all of that could be controlled. Imagine you start actually linking sort of monetary value and the ability to hold money with your character's identity, and you start hiding information and finding things that can't be replicated. So when we're talking about these simple information games, we can have a lot of external information that gets saved and sent simultaneous to using sort of hash trees and other areas to, well, basically allow us to incorporate, say, magic items, weapons, all this sort of silly stuff in games that we can now provably say only exist once.
Okay. Almost like
The equivalent here is
sounds like a
the equivalent
like the
become
like an NFT. So
in a way, yes, but when I did these things in my original sort of patent that I put out that covers NFTs, wasn't meant to be NFTs. It was meant to be things with value and that you could set sort of constraints on the rules, etc. Um, proving things like a virtual baseball card is authentic, proving things such as items that stay with you. Certificates of authenticity was the concept. So this actually goes right back to like early 90s again. Imagine something like, how do I create a digital signature from Department of Motor Vehicles that certifies my information is correct? How do I now exchange partial information on that that doesn't give away my privacy? How do I create a game item and allow the sale of that without any way of copying it multiple times? So this is, of course, where we start doing key schemes and creating hierarchies of keys and proving provenance. So what was it? Now, looking at games, we've got to start building not only the provable games here, but how we own sort of items. May seem sort of silly, but the concept of NFTs is really being misused in that way. This was also a difficulty in sort of the what do you call it? Xerox, virtual life type games. How do you ensure that no one can cheat? So, how do you do it inside?
is
How do
this
you
one of the major advantage of putting a Bitcoin? Because for now we kind of trust whatever with the World of Warcraft, whoever is hosting this, we trust them doing the right job.
Exactly. I mean, well, this is the point. You can be hacked. You can lose your stuff. There's no record. You have to trust all of these game companies. You have to hope that nothing goes wrong. You have to hope that no one hacks it, etc. This is what I'm trying to get at. We can start actually building things, not only corporate, not only sort of goods movement, etc., but complete virtual good side of all of this, that if I've done a task and it's been signed off, then it escalates. An example of some of these things would also be escalation channels, queuing channels, the ability to monitor things without argument. If this occurs, if it works, this is what happens. Here is the test, for instance. So I could give you a number of assertions of different formats, and I could equally give you other ones that you don't know all the information about. So one of the ways of testing, of course, in or even Python, you have an assert statement, and you can check whether the results are correct, right?
Yeah.
Well, equally, I can do something similar in Bitcoin. So imagine now that I want someone to create scripts or codes or something in a high level language, and I want an assert to work. Then what I can do is I could hold give you a number of tests because you need to know what you're testing against, but not give you all of the tests. Any idea why I wouldn't do all of the tests?
I don't know. Maybe you want to hide some information. Or...
Well, no, not even that. What happens if I give you all of the output values that my asserts are going to do?
Then you can cheat and make sure it always passes the assertion. Or...
Exactly. This is one of the things I've been experimenting with at the moment from things like Coursera. Uh, I've actually got a concept that I could do something better without all the ability to cheat or even bypass some of the controls. Right now, some things go by not giving you all of the tests, but even then, as you go through it, you can learn more of them and find them. But if you could have a number of randomized inputs that seed things, it would even give you a way of randomizing asserts.
Okay, I think I'm a little bit not following here. So what do you mean by test and searching here? Is like a Coursera, you take some, let's say, programming course, and then after each lesson, they give you some
Yep.
homework. You have to pass some tests. That's a kind of like a searching. You have to pass, let's say, all the test cases, something. But they cannot give you all the test cases in advance because then you may cheat, right? You just make sure all these pass, but you...
Yeah, and even worse than that, what they do quite often is the same test goes to every student because it's easier, right?
Yeah.
So then there are all these test sites that put things up, and if the same thing's been written 50 times, then well, people will just copy. But what if there were modifications, but you could also have modified versions of information to test and assert so that every student effectively had something that is the same level of difficulty to create a problem for, but equally different sort of results, different data, different outcomes they're going to have to meet. So they can't just all say, oh, it's the same.
How does Bitcoin play into the role here?
So what we can do, of course, is have unlocks and locks built into this. So the student gets a little bit of randomized information. Maybe a Diffie-Hellman sort of exchange gives a secret. That secret aids in creating like a seed. And then they have their own seed that no one else will ever get, that populates data that's provably going to be theirs, that can demonstrate, for instance, if we're doing tests on like machine learning analysis, where we have a data set, we can randomly, well, not so much random, but based on our seeded information, change what we have there and change the required outputs, etc. So just to make it so that we can't just cut and paste.
Okay, so you can also imagine that assert kind of like you can even put into a script, right? So it's almost like a predicate that you have to pass. Okay.
Yeah. So add things like oblivious transfer and other funky topics like that, and off we go. So I've tried to give a lot of concepts. I'm going to pop off a little bit early tonight because I've got a few things and I've got a busy week before I run off to America. But what I want you to start doing is thinking about how we can link different games using scripts and UTXOs as node points and self-calculate the next ones. So if you think about, remember we've had concepts of how to now mask information and sort of thus calculate the next node point that we're going to be able to send to, whether it's XOR or other masks. Now we can actually start having pre-calculated lists of nodes, pre-calculated lists of transaction movements, have a script that allows only some information to be pruned, but not all. We've done matrices, so once we've got a matrice, we can have some graph problems calculated that get fed back into our transaction. And just give you a little bit more to play with.
Mm-hmm. Yeah, it seems not a big game player, but it seems like not this. How would this? Let's say let's just imagine all this are already built, built according to what you have in mind. How does this look like versus what we have now? Like say Warcraft or whatever. I don't know the latest. How does this differ from a player's point of view? Because eventually you want to have players to play, right? So they got to have some benefits, right? Of course, they can trade this, I don't know, weapons or stuff. That's for sure. Also, they may make money.
All sorts of things, but even in these games. So, as an example, we could have what I've given you there. I mean, you shouldn't have too much difficulty getting it into being sort of non-interactive, player A, player B, player A, player B, that sort of thing. But you can even take it further if you integrate layers of bit commitment. Now, imagine now that each node that people are moving to is defined within the rules so that you can't go anywhere, but you can only go to connected nodes. Then each player moving, whether they integrate or meet or something like this, would then have like NI, the node number for player I, player I, because we've got an N player game, chooses a random key. Could be a derived one from their own thing, but still seems random. So KI, player I will then do a broadcast of the value hash of key I concatenated with the hash of node I that they're moving to. That goes to all other players. Everyone else then in this version of it can reveal KI their own and the hash of node I. Each player, well, in software, of course, now will check the node location. The way you do that is you validate whether node I matches what you have. So if you're now on node I and another player's on node I, then in checking the consistency of the revealed hash of all of key I concatenated with hash of RI, you will now know independently whether someone's on the same sort of virtual game node as you in one of these things simultaneously. And so the two-player perfect information game that I've given has now just become a N-player simultaneous play game. So you'll probably need to listen to that multiple times, and I'll probably need to write it out. I don't think I said anything wrong, but remember, no one can change or cheat because the value of hash of node I is not going to ever sort of change. If we do it with a HMAC, we can make it more secure so that we can equally have it exchanged with exchanges of multiplayer HMACs and information. That will now mean that even though everyone's got different information, it never matches apart from the stuff you get from each. So then think even further, logistics are to people in the same place. You don't want to give out information about anyone for privacy. But hey, I know this person. They're here in the same building I am. That sort of all sorts of funky things.
It is one implication can be like the games. I wouldn't say use this kind of like a decentralized. So even like let's say Blizzard or
Yep.
Electronic Arts,
Yeah.
they went bankrupt, and then if you really the players that really want to do it, they can even get their own servers running and just keep going.
Yeah. Exactly.
Okay.
So,
Yeah, then definitely
but
help
think
with
of all the different things you can start doing.
the games you mentioned in the 90s. So if you still put on the Bitcoin blockchain,
I know,
you
I'm
can
old.
still,
What can I say?
you can still play it.
Yeah, exactly. Well, when I was young, Mario was still around, but not in some sort of stupid little kart thing competitively like the kids play now. Anyway, all right, so I'm going to head off, but
Okay.
are you going to be at CoinGeek?
For me, unfortunately, no, because of I don't have the passport, so that's a bummer. Yeah, I think I really wish, but
well.
okay, I will. Yeah, hope to see you in
The
person
silly
soon.
world of
New York
all right.
City. So I know many people
No problem.
that cannot go,
Alrighty.
unfortunately, this time. Okay, enjoy CoinGeek, and we'll talk to you when you come back.
All right.
Okay.
Okay. All right. I'll talk to you when I'm back. Catch you later.
Okay. See you. Okay. Safe trips.
Bye.
Bye-bye.